Hello, everyone. Thank you all for joining today. My name is Amin. I am PhD student here at ISRS department, and I'm working with that student. So for today, I would like to talk about our recent research, which is the title is an efficient distributed multi-agent reinforcement learning for the EV charging network control. So at first, I would like to talk about the agenda of this talk. So at first, I will go through the details of the motivation of this research, and then we'll talk about the system model that we have, about the current and future smart grid system, and then talk a bit about the formulation, not too much because of the sake of the time, so I cannot go through the very details of the research. And then I will talk about the algorithm that we have used, the multi-agent reinforcement learning. And then at the end, I will provide some numerical result and the simulation. So the good news these days is the number of the EVs in the power system area is going to increase. So in the US, people will see this trend that by 2030, so the number of the EV is going to increase. And this is the good news because the EV is clean and it's going to be cheaper in the future. But the bad news with this increase is these EVs, they are the new source of the demand. They are really significant in the demand side. And so there is another challenge that we have here is the dynamic pricing. I will talk about the dynamic pricing. So these two challenges are the bad news that we have with the EV network. So the question that we want to solve is, what should we do if the number of the EVs increase in the system? How we can control it? So the challenges related to the EV networks can be categorized into different categories, subcategories. So the first one is the electricity supply management, which means that a bunch of EVs, a bunch of households, they are connected to a shared transformer. And so if the number of the EVs increase in the system, so it may happen that transformer overload may happen. And that's a huge loss for all participants in the network. So this is one challenge, challenge that we have. The other one is the price uncertainty. So the price scan is going to change in the power system area. In the modern smart grid, the price is going to change from static price to dynamic price, or even the real-time price. And that would be challenging as because right now the current EV charging controller, they cannot work with the dynamic price. They can just work with the predefined price. And the other one is the user behavior. Because so the EV owners, the owners of the EV, so the behavior is uncertain. So we don't know when they want to charge the EV, what are the arrival time, the departure time. And so we don't know the time that they need for charging the EVs. So the whole point in this research is we want to present a distributed control framework for managing the EV network. So the simple question is, if the number of the EVs increase in the system, with considering the dynamic pricing, what should we do? So now I would like to talk a bit about the system model of the system that we have considered. Suppose that this is a residential area. So in the residential area, we have a bunch of households. So this is something like in the reality that we have. Bunch of households, they are connected to a shared distributor or the transformer. Another bunch of households, they are connected to another transformer. So it means that we have the different networks and we have different distributors. So our focus on this research is the interaction between a network and the shared transformer or the distributor connected corresponding to that network. It means that now consider that our focus is the interaction between network one and the distributor one. So let's see what we have. So the interaction between the utility company or the transformer or the distributor and the end user in the traditional smart system is a one-on-one match, the one-on-one interaction. But this interaction, engage is going to change in the modern smart grid as this one. It means that the utility company is engaged with the network of end users, and the end users, they can have information exchange with each other. So this can be a power exchange with arrows or the information exchange, communication. So this is another overview of the system model. So suppose that we have in between the medium voltage, low voltage transformer. From one side, this transformer is connected to the upstream grid or the distribution system. From this side, the other side, this transformer is feeding the end users. And so suppose that each user in this system model has an EV charging controller, and then we put a virtual layer in between, which means that we put AI agent. We locate AI agent for each end user, and this AI agent responsibility is controlling the EV charging of each household. And then these AI agents can have the interaction with each other, can have the information exchange. And they want to control the system. The whole point here is they want to cooperate with each other to maximize their local profit, and at the same time, they should prevent the transformer overload, the shared transformer. But the point here is the current smart EV charging controller in the market, they just work with a predefined price scale. What that means that suppose that you have an EV charging controller, a smart one, and so you plug in your EV, for example, at 2 p.m. and then until 6 p.m. And so that smart one optimizes the charging the EV based on the predefined price. But what happens if the prices can change? Means if the price is dynamic, what should we do? And so the existing control algorithms are not responsive to the uncertainty from the prices, as I said. And so we are looking for implementing the reinforcement learning network for this system to have a control system for this EV charging point. Now, right now, I would like to go through the detail of these physical layers that we see to see what optimization problem we have. Suppose that we have a graph of a network, and the nodes and the edges are denote the user and the branches. So the LIH denotes the consumption of the node I at time H. And so the total consumption of node I at time H. So the LIH defined as a summation of the consumption of all appliances. And then we differentiate between the all appliances and the EV. And so with the lack of generality, we can assume that the other appliances, just for now, assume that the other appliances, they are constant, they have the constant consumption. So we just consider the EV consumption, because the focus of this research is the EV. And so at the end, we have this optimization problem. So we want to minimize the total cost of the system. The CH here denotes the cost function at time H. So, but as I said, we are looking for a distributed control. So this optimization problem can be solved in the centralized fashion, but we are looking for a distributed control of this optimization function. So to do this, we want to transform from the central one to decentralized. Suppose that assume two neighbors, household one and household two, at any given time. If household one consumes twice than the household two, so at that time, the household one will be charged twice than household two. Okay, so using this one and doing some math, so the BIH is the billing amount in dollar to be charged for the household I at time H. And then doing some math, we have this equation. So let's simplify it. We have this one. At the end, we have this optimization problem from the one individual agent perspective. And here we see that if each user wants to minimize the cost, so they need these two information. The first one is the local consumption, LIH, which is okay, it's fine. But the other one is they need to know the other user's total consumption. And this is the information that's not feasible in reality. We cannot share this type of information. Each individual user cannot know the other user's information, the other user total consumption. Okay. So there are some research that they try to solve this problem, for example, with game theory or the other optimization techniques. But here we want to relax this assumption by using the reinforcement learning. So the algorithm that we have used is a cooperative multi-agent reinforcement learning. We use the multi-agent deep deterministic policy gradient. This is the setting of the multi-agent DDPG. So here you see that we have the agent here. So the DDPG, for those of you who may or not familiar, who may not familiar with the reinforcement learning is a technique of machine learning. And in the reinforcement learning, we have the agent, we have environment. So the agent take action, change the environment, and then receive a reward. During the long run, the agent can learn how to react in that environment to maximize the reward. So it means that the agent doesn't have any priori knowledge about the dynamics of the environment, but it can learn with try and error. So the DDPG uses the benefits of the active critic and the benefits of the DQL. So this replay buffer here is the benefits of the replay buffer and the active critic architecture. So the process starts here. The actors select an action, and this action is going to be done with the other action and the joint action going to the environment here and change the environment. And then this process is an iterative process that happens. So during the training, there are some samples from this replay buffer, and then the information goes to the critic and the actor and train them. So the actor is responsible to select the action, and the critic criticize the action selected by actor. So the whole goal of the reinforcement learning is to maximize its return, as this one, J theta. And so to maximize this, which is the expected of the reward, as I said, this is the goal of the reinforcement learning. So the way that the reinforcement learning agent do is to move to using the gradient ascent, moving toward the gradient of this J. So here. And so for the cooperative multi-agent reinforcement learning, there are several variants. We have used two of those. The first one that we call it as an independent DDPG, which means that this is the gradient of the J in the previous equation. So this means that suppose that there is no cooperation. So we train all of the agents independently, and each agent is trained based on the local information. This means that we are ignoring the non-stationarity of the environment. Okay. So the other one is the CTD. There is a powerful framework in the multi-agent reinforcement learning that says that you can assume that you can have the information exchange during the training, but during the execution, there is no information exchange. So centralized training, decentralized execution. So we can assume we have some global information exchange between the agent during training, but during the execution is different. So the thing right now I would like to talk about is to define what are the actions, what are the observations that we have from the environment, what is the reward function. Each agent is equipped with a continuous action set, and we call it as an AI. And this AI represents the power rate of the charging. So the power rate of charging at any given time is the action that the agent select. And so these are the observation that we have from the environment. So the first one, delta V, shows represent the difference between the desired and the current battery state of the charge at any given time. So the battery is charging. At any given time, we can measure the difference between the current battery state of the charge and the expected one that the EV owner needs. So the delta H shows the current time, difference between the current time and the arrival time. So FH is the sample from the price. So they don't know the dynamics of the price. They don't know the function of the price. They just have some samples at any given time. And so the price is a function of the total consumption of the network. And so the PL is an indicator that denotes the EV is connected or not. And we have the departure. So this is the reward function that we have used based on those observations. This is something like the cost, the negative of the cost, because we want to maximize the reward at the end. So let's have some results. So this is the first result that I want to show. So here, this shows a scenario for the 10 agents. In this result, we have 10 agents, from agent 1 to agent 10. And the blue curve, it denotes the centralized training, the centralized execution. The orange ones related to the independent framework, independent agent. And so this shows the average battery level or average battery state of charge. And it shows that in both algorithms, the independent and the cooperation, both they can charge the EV during the charging phase. And this is the requirement that should be met. So here we see that both framework work, but if we go through the details of the action was, if you remember, the action was the charging rate. And again, the blue one related to the CDD or the cooperation multi-agent, and the orange one related to the independent multi-agent. From agent 1 to agent 10, and this y-axis shows the charging rate. And we see a smooth waveform for this cooperation, for the cooperative multi-agent, but we have a lot of fluctuation in the independent ones, which is not good because we are charging the battery, and this fluctuation is not good for the battery life. So, and we see at least 36% reduction in the total variation. And so this is the price comparison for 3 agents. This is for 3 agents, 5 agents, 10 agents, and 20 agents. And we see this fluctuation in the price as well for the orange one, which is the independent one, which means that this is a financial disadvantage for the participant in the network because the price is changing a lot. And so this is another comparison based on the cost for the 3 case of the 3 agents. This is the 5 agent, 10 agent, and 20 agent scenario. And so in all scenarios, we have seen that the CDD outperformed the independent one. It means that in this case, in this special case, the cooperation worked better. So let's have at a glance what we had so far. So I have talked about the challenges and the solution for the EV network. The challenges that we had was the increasing of the EVs in the power system network, which led to the transformer overload, and we try to combat this challenge. And so there are some research questions that we try to address, like how to control the residential EV charging network. And the solution that we provided was the cooperative multi-agent reinforcement learning for this framework. And that's all that they have right now. Is thank you all.
Time for 2 questions. So you have a distributed system, and it takes time for agent A to communicate information to all the other agents. Where does that come into your equations?
Okay, so right now we assume that the communication is perfect, so there's no delay in the communication. And
Can I buy your network then?
Because this is, as I said, the CTD, the centralized training, the centralized execution. The whole point of this one is we can assume we have those information exchange between the agent during the training, which can be in the lab. So it means that in the reality, there is some limits, but there is no information exchange in the reality. It means during the execution, there is no information exchange, just during the training. When we want to train them, we can assume that this is the beauty of this framework. They just assume that during the training, which can be happen in the lab or in the simulation or anything else. So you can assume that this information is exchanging and the agent can learn based on those information. And here in this phase, we assume that this information, this communication is perfect.
So I'll do one more. So you described a distributed, in some sense, a distributed control system. And there are lots of distributed control systems. What's different?
So the difference between this one, as I said, and the rest of them is the priority knowledge about the dynamics of the system. So the reinforcement learning do not need the dynamics of the system. It means that we just take an action. It means an input, output. This is a trial and error. There is no prior knowledge about the dynamics of the system. Maybe in other framework of the distribution system, so we need some information from the dynamics of the system, but here we do not.